Hi guys, this is practice set 1, points back step 1. And so you should have in front of you your salmon colored packet, AP Calculus exam topics to look for part 2. And we're going to cover the following exam topics that you should be looking for, like doing some examples of them. This could be a long video, so if you need to watch it in more than one sitting, just make sure you're keeping track of like where you left off, like at what time you're pausing the video. But if you need to, take some breaks while you're watching it, you can. I don't think it'll be as long as the first salmon colored packet video, but it might be kind of long for a video. So the first topic is absolute extrema. So guys, whenever you are, so absolute extrema, absolute extrema will always be on an interval, and you will need what's called the candidate's test. Okay. So I'd write that down. So here's the example. The rate at which the amount of water in a tank changes is given by this. So this is a rate of change. So this is the derivative of something. If there were initially 20 gallons of water in the tank, find the absolute maximum and minimum amount of water in the tank from 0 to 2.5 seconds. Okay? So they want absolute max and min, and they're giving us the interval that they want it on. So what you've got to do is, so I would do this, guys. I would first let, so let's let A of T equal the water in the tank, okay? And let's write down what they're giving us. They're telling us that initially, whenever you hear this word initially, this means at time 0. So there were initially 20 gallons of water in the tank. So they're telling us that A of 0 is 20. And guys, we can't find, so when you're going to use the candidates test, so the candidates test works like this. So over here we'll get ready for the candidates test. You make a table of values. So we've got T, that's our input, and then our output Y is going to be given by A of T. And so here it's called the candidates test because here you list all of the candidates for which an absolute max or min might occur at. And the candidates are always the endpoints of our interval. So the first candidate will be 0. The last candidate will be 2.5. And then the way that you find the interior candidates between them is you need critical numbers. So need critical numbers. So that would be where the derivative is 0 or undefined. All right, so we'll get there in a minute. Now, because I know that I'm going to be using the candidates test and having to get the outputs for these inputs, so I need to get the the outputs here. What I need to do is I need to find A of T. And guys, so let's write down this information. So A of T equals, so remember, we're always asking ourselves, so at this point I need to ask myself, for A of T, do I need a limit, a derivative, or an antiderivative? Do I need a limit, a derivative, or an antiderivative? Well, they've given you this function, which is the rate of change of the water in the tank. So this is A prime, actually. Okay, so this right here is actually A prime. So the answer to the question, do we need a limit, a derivative, or an antiderivative, is we need an antiderivative. I can't take the antiderivative of something like this. There's not a formula for it. There's no technique for it. When you can't find the antiderivative, you've got to use the antiderivative with an integral formula. So A of T is going to be we know A of 0, so it's going to be A of 0 plus the integral from 0 to t, and then in here is going to go a prime of w dw. So we're going to be using this to get the outputs over here. And by the way, a of 0, guys, I'm using a pencil this time. I don't normally, but a of 0 is 20. Okay, so that's our antiderivative right there. That's how we'll get our output values. Now, for the critical numbers in here, remember that the critical numbers are where a prime of t equals 0 or is undefined, all right? So this is a problem on a calculator section. So I'm going to take my calculator and I'm going to plug in. So I've got to find where a prime of t is 0 or undefined. And remember, a prime is r of t. So I'm going to graph that. So I've got sine of 1 plus x squared, and I'm going to graph this on my interval that I'm on, because I want the critical numbers where this is 0 or undefined on that interval. So I'll go to my window, x min is 0, x max 2.5, and then I'll graph it. 1, 2. Okay, so I've got 2 points. So this is the graph of r of t, which is a prime. So I've got two critical numbers here. And to find them, I'm going to use this 0 feature on the calculator. Okay, so left bound, right bound, enter. Okay, so my first critical number is 1.463, blah, blah, blah. It's an irrational number, so I'm going to store it for later use. So I go to my home screen, I hit X. My calculator remembers that I just found that. And then I'll store it as, I won't use A because I'm already using A for something, so I'll use, whoopsie, I go store, so I hit, the store button is right up above on. And then I go B. Oh, crap. Shoot. All right, so that was X. Store, there we go. B. Okay, so now that's stored as B for later. And this is going to go in my table. All right, so I'll say like B right there. And then maybe I'll say like here, B, I don't know, somewhere else. I got to tell my reader what these numbers are. So B is 1.463 ... So I'll say that for my reader for later. Okay, now let me find the other one. Second, geez. And guys, a good thing, and I've noticed some of you doing this, which is great, you could always like try to go ahead of me and then see if we end up at the same place when we're doing these. I think that'd be a great idea. But you know, however you feel you learn best. Okay, so there's my second critical number. So again, home screen, hit X, and then I'll store this under C. I haven't used C yet. Okay, so C, and then C equals 2 that I'm using a pencil, 2.298 ... Okay, now we're going to get these outputs. The smallest output will be the absolute minimum. The biggest output will be the absolute maximum. All right, so I've got A of 0 equals, actually guys, they told us that. They already told us A of 0 was 20, so that's easy. Now this one is going to be A of B equals 20 plus the integral from 0 to B. All right, I'm just using my antiderivative over here. And then inside, I'm putting A prime, which is really R, so I'll say R of W. You could leave it A prime, dW. All right? And then, so I'm just going to write out the integrals for the other ones also. So I'll have A of C equals 20 plus the integral from 0 to C, R of W dW. And then A of 2.5 equals 20 plus 0 to C, R of W dW. Okay, so now I'm going to find them. So I go math 9. Math 9. Whoopsie, let me do 20 first. So 20 plus math 9. 0 to B. And then sine of 1 plus W squared. So sine of 1 plus X squared. Yeah, guys, I really will not blame you if you, you know, I think it might be a good idea to watch this video in chunks. Okay. Alrighty, so this is 21.179. Okay, then I do the other one. And now I can just go second enter, guys, and then just go all the way. The only thing I'm changing is that upper limit of integration. So I just go back up here, and I'm changing that B to a C. Okay, and then I get 20.653. And then finally I'll change it to a 2.5, that upper limit of integration. All right, 20.742. 20.742. So the answer is, find the absolute max and min. Okay, so the absolute max is 21.179 gallons, and the absolute min is 20 gallons. All right, so let's say that nicely. So absolute max, and then let's say A of B equals 21.179 gallons. And then absolute min is A of 0 equals 20 gallons. Okay, that was a lot of writing, guys. Sorry for that small space. Okay, if you want to pause the video here, go be my guest. I'm going to keep going because it'll just be easier, I feel, to, you know, we won't have to be searching for all these videos. Okay, I'm going to push ahead. Absolute value functions. Alrighty, guys, so here I have, we're going to take a limit, a derivative, and an antiderivative. Those are the themes going on in calculus. So I'm going to take each of these of a function that involves an absolute value. All right, so I'm just going to show you how to handle this. Alrighty, so if you basically handle them all the same way, guys. You take, if the function involves an absolute value, you take it and rewrite it as a piecewise function, and then those pieces will not have absolute values anymore, and then you can kind of think it through that way. Alrighty, so I'll go as efficiently as I can, but this is, you know, I don't want to go too fast and sacrifice any understanding. So first of all, you've got to take the input of the absolute value, which is in this case x minus 1, and you've got to figure out where it's positive and where it's negative. So in order to figure out where things are positive or negative, we first figure out where they are 0 or undefined, because those are the potential places where they would change sign. So this is 0 at 1. Okay, to the left of 1, x minus 1 is negative, and to the right of 1, it is positive. So I can take the absolute value function. So I can take this, let me go like this, no. All right, let me go down here. So I can take x minus 1, the absolute value of it, and I can rewrite it. Remember, absolute value is always positive, so on the negative interval, if I negate the input, it would be positive. So I go negative x plus 1 for x less than 1. And then on the positive interval, the absolute value is just the same as the input. So x minus 1 for x is greater than 1. Now, this is defined at 1, so we've got to do an or equal on one of them. It really doesn't matter which one. So guys, if that's the absolute value part, then for the, for the whole thing, we can write it like this. Oh, and actually, I'm going to factor the top. You should notice that difference of two squares there, guys. And I'm factoring it because things are going to cancel. So this is going to be equal to, for x less than 1, it's going to be equal to x minus 1 times x plus 1 over negative x plus 1. And then for x greater than or equal to 1. No, it can't be or equal to. Duh, that's not defined at 1. I'm sorry. Yeah, 1 would make the denominator 0, so it's not defined at 1. My bad. So we do have to leave it like that. Okay, so x minus 1, x plus 1 all over x minus 1. And then those cancel. And then these cancel. No, they don't. Not those. I'm so glad I'm using pencil. These ones cancel, but they cancel to make a negative 1. Okay, because this is x minus 1 and that's 1 minus x. X minus 1 and 1 minus x are like perfect negatives of each other. They'll cancel to make negative 1. Okay, so now I think of the left-hand limit and the right-hand limit. So I'm kind of working backwards here, but so I'll go as x approaches 1 from the left, as x approaches 1 from the right. And then, so y will be approaching, so 1 from the left, I'm dealing with this, top piece. So it's going to be negative, plug in the 1 there, so you'll get negative 2. And then for x approaches 1 from the right, I'm dealing with that bottom piece, so I'll get y approaches positive 2. Guys, the left-hand limit and the right-hand limit are not equal. So that means that this limit does not exist. Okay, now let's do a derivative one. So we're taking the derivative of this absolute value function. You have to handle it, whether it's a limit, derivative, antiderivative, any absolute value function you see, no matter what you're doing to it, take it and split it up as a piecewise function, okay? So I'm going to take the input of the absolute value just like I did before. So 9 minus x squared, that actually factors, that's a difference of 2 squares. So I'm just going to factor it right away because I'll have to anyway soon. And then I do a number line. Okay, so I've got negative 3 and positive 3. And then I do, the interval tests. It goes negative, positive, negative. Okay, just like that. And actually, guys, I just want to point something out. So the graph of 9 minus x squared without the absolute values looks like that. All right, it's an upside down parabola. When you apply the absolute value to it, I just think this is neat. When you apply the absolute value to it, it takes the negative parts and reflects them over the x-axis like that. So this is actually the graph that we're working with. And actually, now that I've shown you the graph, it's not even going to be differentiable there because we've got sharp corners. Remember, at sharp corners, a function is not differentiable. The function exists, it's continuous, but not differentiable. That's why just because something's continuous, it doesn't mean it's differentiable, because it could be like a sharp corner, just like there. So this derivative doesn't exist anywhere, but we can take the derivative of some of it on some of its domain. Okay, really we could take the derivative of it everywhere, but at negative 3 and positive 3. Okay, so let's express this as a piecewise function. So we've got, this is absolute value of 9 minus x squared equals, we're going to have 3 intervals, so 3 pieces. So on this interval, we need to negate it because the input would be negative, so if we negate it, then it's positive. Negative 9 plus x squared. That is for x less than negative 3. Okay? And then between here, it'll be just regular because it's positive anyway. Negative 3 less than x less than 3. And then we've got to negate it again on that interval. Negative 9 plus x squared for x is greater than 3. Now, remember before when I messed up and I did or equal to even though it wasn't even defined there because that would have made the denominator 0? This one is defined everywhere. Okay, so I need to include, so I'll just do or equal to's there, okay, because it has to be defined at 3. Alrighty, so guys, the way that you take the derivative of a piecewise function is you just take the derivative of the part. So the derivative will be piecewise. So the derivative of this is going to be, the derivative of this top piece is 2x. The derivative of the middle piece is negative 2x. Bottom piece is 2x. And this will be for x is less than negative 3. This will be for negative 3 is less than x is less than 3. Yep. Guys, I'm not including them because, as we observe from the picture, the derivative doesn't exist at 3 and negative 3. Okay, that's why I'm not doing or equal to. The derivative doesn't exist there. And then x is greater than 3. All right, I promise I'll speed this one up because I feel like we have the most experience with doing this with antiderivatives. Now, actually, guys, this is not... Okay, this is not really an antiderivative. This is what's called a definite integral, which means the area under the curve. And people conflate integrals and antiderivatives because the fundamental theorem of calculus says that you take the antiderivative to find the area under the curve. So the two concepts have really become conflated over time. It's really not a huge deal, you know, if you mix them up in your head, like you're going to get the right answer. But Mr. Romer was always very adamant about them not being the same thing. And I think he's absolutely right. When I was first learning calculus, I didn't really know or care about the difference. I don't feel like anyone ever mentioned it. But anyway, this means the area under the curve. I'm calling this antiderivative because you would need to take the antiderivative to get this. Okay, so this is like the category. Antiderivatives are the category that definite integrals fall under. I won't follow through on this whole problem. And again, like I said before, go ahead of me with this. It might be more interesting for you that way. So I'm going to take the input, I'm going to take the input of this absolute value. Yep, and I'm going to find out where it's 0, so I'm going to factor it. I've already factored it, guys. We probably should practice factoring because you don't want to get tripped up on that. I mean, I think you guys are pretty good factorers anyway, but we could probably just sharpen it up before the test anyway. But that's how that factors. And it would be a good exercise to make sure you understand that. Okay, and then I'm just skipping a lot of explanation here, but you end up with that. So I can take this and separate it into 4 separate pieces. On the negative integrals, I will negate the input. On the positive, did I say integrals? On the negative intervals, I will negate the input. On the positive ones, I will keep it. So it goes negative x to the third plus 5x squared minus 6x. And then I keep it. So x to the third minus 5x squared plus 6x. Then I negate it. And then I keep it. All right. And then this is for x is less than 0. 0 is less than x is less than 2. 2 is less than x is less than 3. 3 is less than x is less than, no, just 3, just x is greater than 3. Or 3 is less than x. Alrighty. Now this is defined everywhere, so I've got to include some or equal to's. I'll include this 0. I'll include that 0 there. I'll include that 2 there. And I'll include that 3 there. Okay, so, guys, I'm not going to follow through on the whole problem. But if you were to do this with a calculator, just do Math 9, plug that in. But I'm assuming we're doing it by hand, and that's why we would even need the antiderivative. And you would just split this up into separate integrals. Now, x is less than 0. We don't even really need this first part. We just need these ones. So it's going to be the integral from 0 to 2 plus, you know, of that piece, plus the integral from 2 to 3 of this piece, plus the integral from 3 to 4 of the last piece. Then you'd use the fundamental theorem. Brackets underneath, antiderivative inside, subtract. Alrighty, again, guys, feel free to pause this and come back to it later. Okay, rate in, rate out. Okay, I guess these come up a lot on the AP Calc exam as free response problems, and they're pretty nice. It's kind of easy. If you have something that is changing, and there's like two opposing rates acting on it, the best way of thinking of it probably is like water or something. Like, so I'll just read the problem because it does a good description. So a water tank at Camp Newton holds this many gallons of water at time t equals 0. During this time interval, 0 to 18 hours, water is pumped into the tank at a rate of this gallons per hour. During the same time interval, water is removed from the tank at this rate. So this is a rate in, rate out problem. Okay, we've got the rate of water going in, we've got the rate of water going out. All right, rate in, rate out. Is the amount of water in the tank increasing at time t equals 15, why or why not? So we've got the rate of water going in, we've got the rate of water going out. We need to consider the rate of change of the water in the tank. And what that's going to be, that rate of change is just going to be the difference between these. It's going to be rate in minus rate out. I'm pretty sure. It wouldn't be rate out minus rate in. Yeah, I'm like sure it's that. Rate in minus rate out. Okay. Now, okay, so anyway, let's do this. So I'm going to let, it's never a bad idea to like define a function. So I'm going to let A of t equal the water in the tank. Okay, so that's the amount of water in the tank. If we are asked about the amount of water in the tank increasing, you want to be thinking of like Susan's table. If you hear increasing, decreasing, inflection points, concavity, max, mins, any of that, Susan's table stuff, guys. So increasing, so A of t would be increasing if A prime of t were positive. So that's what we've got to figure out, guys. So we need A prime. So A prime of t. And the way that you do it is you do the rate in minus the rate out. All right? So we've got A prime of t is equal to W of t minus R of t. So it's equal to 95 radical t sine squared of t over 6 minus 275 sine squared of t over 3. Okay, so that's A prime of t. Now they're asking, is the amount of water in the tank increasing at this time? Well, let's plug this in. Let's find A prime of 15 and see if it's positive. If it's positive, the answer is yes. If it's negative, the answer is no. Okay, so we'll go like this. So therefore, A prime of 15. It's kind of tedious to plug that into your calculator. I already took the liberty, and it is negative 32.674. Guys, if they ask you a yes or no question, I have learned that you need to answer clearly yes or no. So, is the amount of water in the tank increasing? No. So don't just be like, it's decreasing. Say no. Yes. Okay, so no, and then because y, A prime of 15 is less than 0. All right, so that's part A. Now, part B. Oh, and all the while, guys, we are asking ourselves, are we taking a limit derivative or antiderivative? The answer here was derivative, but we didn't really have to differentiate anything because we were already given the rates of change. So to the nearest whole number, how many gallons of water are in the tank at time t equals 18? So, all right, so that was part A. So part B, we want A of 18. Remember, I let A equal the amount of water in the tank. We want A equals 18. So you ask yourself, am I taking, so we've got A prime, and we want a of 18. So am I taking a limit, a derivative, or an antiderivative? The answer is antiderivative. We are on a calculator section. These are very complicated functions. Don't bother trying to use any rules or techniques here. Just know the antiderivative with an integral formula. So we've got a of t is equal to a of whatever, a at whatever time we know a at, plus 0 to t, and then a prime of w dw. Okay. And so we want a of 18, and that's equal to a of 0 is what? 1200 plus 0 to 18, a prime of w dw. All right? And we have already told our reader what a prime of t is. Okay, so I don't think there's any need to like write it in there. You could be like, I guess you could be like big W of little w minus capital R of little w, but this is good enough. We've already been clear to our reader what a prime of w is. And then you plug this in your calculator, Math 9, and you get this, 0.159 gallons. Alrighty guys, feel free to take a break. This is going to be a long one. Okay. Oh, God. Alrighty, next. So the derivative of an antiderivative with an integral. Alrighty. So what you need to know is the antiderivative with an integral formula. So you would need to know that f of x equals f of a plus the integral from a to x f prime of w dw. All right, so, and the input of the integral is the derivative of this. The input of the integral is the derivative of that. All right, that's the key observation here. And guys, if I erased this f of a, if I erase that f of a, then this just becomes a special case of that formula, okay? Alrighty, so the input is the derivative of that, all right? So now that we have that clear, down here they're asking for f prime of x. So f prime of x. Well guys, this looks exactly like this. This is an antiderivative with an integral. That's an antiderivative with an integral. Where do you find its derivative? It's the input of the integral. But they want f prime of x, so that top, that upper limit variable, we've got to plug back in. So this is 1 over 2 plus e to the x. So it really is as simple as that. It's kind of like the integral stuff just cancels, basically. Alrighty, now this next one is a little bit trickier because we need chain rule, because this is not just an x up there. This does not match exactly our antiderivative with an integral formula. This needs to be just x. This is an x squared. But we can still handle this, but it's actually a chain rule situation. So in, out. All right, so the inside function is x squared because that's where the input goes. The outside function is the integral from 1 to blank. Oh, whoa. Nope. Cosine of t dt. All right. So the derivative of this is just 2x. The derivative of this, remember the way that this worked is, you know, we just, the input was the derivative, and then we just switched that variable for that upper limit. Okay, so the input's the derivative, but we switch the variable in it with the upper limit. So this input, cosine t, that's the derivative, but we need to switch the variable with the upper limit. So this is going to be times cosine of blank. And as usual with the chain rule, what goes back in there, what used to be in there to begin with, because it's this blank, 2x squared. Okay? Yeah, I hope that's clear, guys. Cosine of x squared. If it's not, I could try to explain it a different way. Alrighty. Verifying differentiability. Okay, guys, okay, so we want to verify that this is differentiable. So what we're going to do is we're going to find its derivative, and then we're going to see if the left-hand limit of the derivative is equal to the right-hand limit of the derivative at the point in question. So, and actually a lot of times first they want you to show that it's continuous, but I don't know, we know absolute value functions are continuous already. I mean, it's probably not a bad idea to prove that, but I actually don't really think it's necessary. Okay, so in your notes early when I first taught this, I did first prove it was continuous, but all right, 3. Alrighty, so I took the input of the absolute value and I figured out where it's negative and positive. So that means that f of x is equal to negative x plus 3 for x is less than 3 and x minus 3 for x is greater than 3. It is defined at 3. This f is defined at 3, so I've got to throw in an or equal to somewhere. On either one of them. Don't do it at both, but on either one of them. Okay, so now, so if that's what f of x is, then f prime of x is equal to negative 1, because that's the derivative of the top part for x is less than 3, and 1 for x is greater than 3. I'm not going to throw in an or equal to. I'm not going to throw in an or equal to unless I can conclude that the derivative does in fact exist at 3. Okay? Because it won't exist if the left-hand limit and right-hand limit don't agree. So, so I go the limit as x approaches 3 from the left of f prime of x. This is equal to, so approaching 3 from the left would be this side, so it's approaching, it's staying constant at negative 1. But we can still say it's approaching that. And then from the right, f prime of x equals positive 1. Those are not equal. So it's saying explain, so the answer is no. Okay? So I will say no, or period. Since the one-sided limits as x approaches 3 are not equal for are not equal for f prime of x, comma, f of x is not differentiable at x equals 3. Guys, this is yet another example of how just because a function is continuous does not mean that its derivative exists everywhere. All right, and if you graphed this, you'd have a sharp corner at 3. Okie dokie, here is the next one. Area and value, we got 2 more sections. Okay, so area and value. Let me get a drink. Okay, so what I'm going to do, I'm going to give a little bit of a different approach. I don't know. I feel like you can use those charts that I was teaching, guys, absolutely. But I felt like a lot of the logic and problem solving kind of got lost in the charts. Like, I don't know. It was just kind of a lot to remember, I think, for some people. So if you like them, please, if they don't confuse you and you feel confident with these problems using them, then use them. But I'm going to revert to these formulas. So we need to know these. We've got 2 area formulas, 2 integral area formulas. we've got two integral volume formulas. The top two are with respect to x, the bottom two are with respect to y. How do you know which to use? It depends on whether you're finding area or volume with vertical slices, slicing through the region vertically, or slicing through the region horizontally. Okay, so, and guys, read the problem. So we're going to read the problem and then ask area or volume and which formula. Okay, so find the area bounded by the three curves below. All right, so I guess let me graph the region first. All right, so we've got this. This is y equals radical x. That's 6 minus x. Here's the vertices of the region. Okay, and then I'll shade that in. Okay, so that's the region. To save time, I'll tell you these points. That's 0, 0. That's 6, 0. And that's 4, 2. Okay, so first we're going to ask area or volume. They said very explicitly, guys, find the area. So this is area. Now we just have to decide which of these area formulas that we're going to use. So are we going to slice through this region vertically or horizontally to find the area? And actually, guys, you can really do either, because every vertical line only hits each graph once, and every horizontal line only hits each graph once. So you have some freedom here. You could use either of those formulas. The advantage to using the horizontal slices is that you'll be able to just use one integral, except you'll have to convert everything in terms of y. If you do vertical slices, you're going to have to use two integrals because you'll be doing top minus bottom, and they'll switch here. All right, so anyway, I will do vertical ones. Okay, and I'll draw two because I'm going to have, and guys, an integral, by the way, so imagine that these are like really thin rectangles. We're adding up an infinite amount of really thin rectangles. That's what an integral can do for you. And putting something in an integral adds up an infinite amount of those things that are infinitely small. Alrighty, so we're doing area. And since I'm using vertical slices, I will be using, and remember, vertical lines hit the x-axis. So that maybe will help you remember that. Horizontal lines hit the y-axis. So that's why in terms of y there. So area, and I'm using this formula. All right. So it's going to be the integral from 0 to 4. Top minus bottom is radical x minus 0, so just radical x, plus the integral from 4 to 6. Top minus bottom is 6 minus x minus 0 dx. All right, and then we could just plug this in our calculator unless it says that we can't use one. And the answer is 7.333. Okay, next. Read the problem and then ask area or volume and which formula. Find the volume of the solid whose base is bounded by the circle given and the cross sections perpendicular to the x-axis are equilateral triangles. Guys, let's write this down. I'm making you flashcards soon, and we really should memorize this. If you've got an equilateral triangle, a lot of you I've already gone through this with, but if you've got an equilateral triangle, let's call every side A. All right. If you want the area of this triangle, you need the height. All right. So I'll drop a height like that. And there's many ways that you could prove this, guys. But the height of an equilateral triangle is always radical 3 over 2 times the base. Always. You could prove it with trig. You could prove it with Pythagorean theorem. You could use similar triangles to prove it, but it's always the case. It's way easier just to memorize that than to have to try to figure it out every time you encounter the area of an equilateral triangle. Okay, so the first thing that you always want to do is draw the picture. Okay, so this is a circle with radius 3 and the center 0, 0. Okay, the radius is 3 because remember you take the square root. All right, so this is 3, negative 3, 3, negative 3. Okay, and guys, I would always shade the region too. Okay, so that's the region in the plane that we're working with. And this is one of those problems where you've got cross sections coming up out of the paper. Remember when I did the Play-Doh and I had the stuff like coming up out of the paper in the video? That's what this is like. All right, so the cross sections are perpendicular to the x-axis and they're equilateral triangles. So I need to have an equilateral triangle coming up out of here perpendicular to the x-axis. So I'm just going to draw one. And I do not know how to draw do perspective or anything. I don't even know. I was trying to slant it so it looked like it was 3D, but I don't know how to do that. So that's an equilateral triangle. And okay, so now we know that this is volume. And then you ask what formula. Well, guys, these slices that we're using, which are triangular slices, they are vertical slices. Vertical lines hit the x-axis, so everything's going to be in terms of x. So the volume is going to be given by this formula. X equals A to B. And this here, guys, A of x, I'll just say what this stands for. This stands for the area of cross section with respect to x, though, so as a function of x. So once I find A of x, guys, I've got this. So A of x is going to be equal to 1/2 base times height. All right, let me leave more room for my base and height because it's a triangle. So 1/2 base times height. This is the base. It's vertical, so you do top minus bottom. So I need top minus bottom. So I got to do the top half of the circle minus the bottom half of the circle. And also I need everything in terms of x. So if I solve for y, I'll have that. So I'm going to go a little bit fast here, but you're going to end up with the top half being y equals positive radical 9 minus x squared. And then the bottom is y equals negative radical 9 minus x squared. If you don't understand how I got that, you should try it yourself. So top minus bottom, which is this length, is this radical minus negative the same radical. So you end up with this radical plus that radical, and they're the same radical, so this is 2 radical 9 minus x squared. Alrighty, so that's the base. Now the height, this is an equilateral triangle, so we can use this fact over here. The height is radical 3/2 times the base. So I just go radical 3/2 times the base, which I just found. 9 minus x squared. Okay. Now, those 2's cancel, and you end up with the volume being the integral lowest y, lowest x, leftmost x, rightmost x. And then inside the integral, we've got radical 3, and then 9 minus x squared squared. And you might notice that this is just 9 minus x squared. dx, plug it into your calculator. 62.354. Okay. Oh my God. This is the third to last problem. Read the problem and then ask area or volume and which formula. Let R be the region bounded by y equals radical x, the line x equals 16, and the line y equals 0. Find the volume of the solid obtained by revolving around the y-axis. Okay. So, draw the picture. This is y equals x. Let's say that's x equals 16. Okay, so here is our region. That's 16, 0, 0, 0, 4, no. 16, 4. Okay. Now, guys, when you have these revolution problems, okay, like, remember when I was using these before? When you're revolving like this, Okay, it's going to end up like the region will end up being reflected over at some point. Like it's sweeping all through the space all around, but at some point it's going to be ending up like over there. So I think like to draw a nice picture, we should first, so this is being revolved around the y-axis. We're revolving around the y-axis. I'm going to first, so I'm imagining this revolving around, and I'm going to have a better picture, I think, if I like reflect that region over, okay, just like that. All right, and it's still like going around and around and around. Yeah, so it's going around and around and around, like so. All right, and this is volume. And now I got to try to draw the cross sections. All right, so the cross sections were triangles here. Here we just had these like flat rectangles. That was 2D. But now my cross sections, anytime you're revolving, the cross sections are circular. So, and the center of the revolution is on this line. So I'm going to put a dot there. That's going to be the center of my cross section. And then since this was the original region, this is just the image of it when I reflected it. Since this is the original region, I'm going to draw my radius to that. So I draw it, and then I've got this empty space between the region I'm revolving and the center. I've got this empty space right there. So that means I'm going to have a donut. And then, so that's going to be little r, and then we're going to have big R is like the whole thing. And then, I'm not the best artist, guys, but I think that this is, you know, doesn't look that bad. So I'm revolving the little, when I revolve this part, it ends up looking like that, and I just have like that empty space in the middle. And then I revolve the rest of it, and it's looking like that. And this is all empty space, but as the region sweeps through the air, you know, this will all be like filled in there. Okay? And then you just have infinitely many of these stacked on top of each other, and they create this like solid shape with a, you know, empty and stuff in the middle, like a weird like bowl sort of thing. Okay, so the volume, which volume formula are we going to use? Which one is it? Well, these slices, guys, all of the slices are horizontal slices. They're perpendicular, or they intersect the y-axis, so we'll be doing everything in terms of y. So the volume is going to be this formula. Y equals A to B. The area in terms of y of a cross-section dy. So I got to find down here area in terms of y. It's a washer or a donut. So the area of this is pi big R squared minus little r squared. It's been a while, but okay, so it'd be pi r squared if it wasn't a donut, if it was a disc. But if it's a donut, it's pi big R squared minus little r squared. Now for the big R, okay, big R is from the center to the end of the region. So I've got to do right minus left. Oh, and by the way, I need everything to be in terms of y. Okay, so instead of y equals radical x, I'll say x equals y squared. Okay, that's what that part is there. Okay, so I need this length, big R. So right minus left is 16 minus 0. So big R is just 16. Little r is the empty space radius. Right minus left, right minus left. So y squared minus 0. So that's just y squared. Okay, so my volume is going to be the integral. All right, so y value. So the lowest y is 0, the highest y is 4. And then this is pi. 16 squared is 256 minus y squared squared is y to the 4th dy. And I got this already. 2573.593. Okay, the last page. Jeepies, this is a lot of talking. Alrighty, so differential equations. Okay, what is a differential equation? Let me try to describe it. Okay, so it's an equation with a derivative. And x's and y's mixed up. All right? So there is a derivative. You know it's a differential equation if there is a derivative already in there in the equation, and then you also, in addition to that, have x's and y's all mixed up. Okay? And then the solution is a function y equals f of x. Okay? And the way that you solve them is like this. All right, so this is a differential equation because here's the derivative. There's a derivative involved, and then I've got x's and y's like mixed together here. The first thing you've got to do is separate the x's and y's. So I'll go dy equals, I'm going to do it in 2 steps. You could do it in 1 though. X to the 4th, y minus 2 dx. Then I'll divide both sides by y minus 2, so I get 1 over y minus 2 dy equals x to the 4th dx. So first you separate the variables, then you take the antiderivative, which is another name for an indefinite integral. People usually just say the integral. Then you take the integral of both sides, which is the antiderivative. Guys, over here, think of so now we're taking the antiderivative. So am I taking a limit, a derivative, or an antiderivative? That's what you're always asking yourself. And the answer here is an antiderivative. You need to know your formulas and techniques. This is a fraction, so I go through all of my fraction techniques, and f prime over f jumps out at me. And yes, if this is f, f prime is 1. So this is f prime over f. So you need to know that its antiderivative is the natural log of the absolute value of f. All right, so that's the antiderivative of the left side. Now the right side, antiderivative. 1/5 x to the 5th plus c. Don't forget the plus c, guys, on the right. You don't need it on both sides, just on one. Okay, now when they ask for the solution, y equals f of x, they are telling you, I wish they would just say solve for y, but this means solve for y. Because so often in AP Calc you don't have to simplify, but here they are telling you to solve for y. We're going to have to find c at some point using this initial condition. I would hold off. Okay, I wouldn't find it right now because that natural log is going to complicate things. So let's hold off on that. When you've got a natural log involved, hold off on finding c. If there wasn't the natural log, we could do it now. You've got to roll up the log or convert to exponential notation, however you like to think of it. So this is going to be the absolute value of y minus 2 equals e to the this, so 1/5 x to the 5th. And then if you're adding in the exponent, that's the same as multiplying, like bases. So I can write it like that. Okay? And then I could say that y minus 2 is equal to k e to the 1/5 x to the 5th, but tell your reader where this k came from, where k is equal to plus or minus e to the c. Okay? Then you could add 2 to both sides, so y is equal to k e to the 1/5 x to the 5th plus 2. Now, this is not solved for because x is the input variable. K is a constant. We have to know what this is, and that's when you use the condition that they give you. So it's at this point that I plug in 0 for x and for y, and you just end up with this. So k is -2. So the final answer is that y equals -2 e to the 1/5 x to the 5th plus 2. Okay, so that is the solution, y equals f of x, to the differential equation. So here's the last one, guys. You will never have a video this long again. So this one here, I've got to separate the variables. It's a differential equation because we got dy dx, x's and y's mixed together. I'll do it in one step this time. So y dy equals x plus 1 dx. Separate the variables. Take the antiderivative, okay, or the integral. This is 1/2 y squared equals 1/2 x squared plus x plus c. Don't forget that. Now, I held off on finding c last time because of the natural log, because that was going to complicate things. This time, you know, it's not going to be really any more or less complicated if I plug in this initial condition now or later. So I'm just going to do it now. So 0 in for x, -2 in for y. Over here, okay, so we got 1/2 -2 squared equals c. So c is equal to 2. So we've got 1/2 y squared equals 1/2 x squared plus x plus 2. You're not done because they asked for the solution y equals f of x, which means they want y solved for. So I'm going to multiply both sides by 2. Y squared is x squared plus 2x plus 4. Take the square root of both sides. Y equals plus or minus radical x squared plus 2x plus 4. But the question is it the plus or the minus? Well, that's when you look at the initial condition. Guys, the initial condition said that f of 0 was -2. All right? So if I plug 0 in here, I get radical 4. Radical 4 is 2. I want it to be -2, so it's got to be the negative one. So y is equal to negative radical x squared plus 2x plus 4. Okay, guys, I hope I never went like slow-mo during this video. Or, I don't know, maybe that would have made it more interesting. But there you go, guys. Good job. This might be our longest video ever.